Welcome to our discussion of evaluating measurements. In this lesson, we will define accuracy and precision, interpret the accuracy of a measurement using significant figures, and communicate measurements in scientific notation. Before we start evaluating measurements, we first need to define two terms that are very often used interchangeably when talking about measurements, but are actually quite different from each other: accuracy and precision. Accuracy is how close a measured value is to the actual value, while precision is how close the measured values are to each other. So in order to determine accuracy or precision, we need to know the actual or the accepted value of whatever it is we're measuring. Let's take a look at these dartboards to clarify the differences between accuracy and precision. So in this example, our accepted value is the bullseye. So in the first target, we have high accuracy and high precision. Our darts are all close to the accepted value, or the bullseye, and the darts are all close to each other. Our, quote, measured values are close to each other. On the next dartboard, we have low accuracy because none of our darts are close to the bullseye, but we have high precision because all of our darts are clustered together and are close to each other. In the third dartboard, we have high accuracy but low precision. Many of our darts are either on or very close to the bullseye, but they're not necessarily really close to each other, so our precision is low. And finally, in the last dartboard, we have low accuracy and low precision. Our darts aren't really close to the bullseye, and they're also not close together. So how accurate can our measurements be? Well, they can only be as accurate as the tools we use, and there's always going to be a certain degree of uncertainty, and that's okay. It's to be expected. In fact, the last digit of any measurement that we take is always going to be estimated. So let's take a look at these three tools as an example. Even though our measurement lines are between the marks on the tool, it doesn't mean that our tools are useless for this particular measurement. It just means that we have to estimate that final digit. And because everybody's different, there is going to be variation because everyone will estimate a little bit differently between the marks on an instrument. But that is going to make up our accepted and expected degree of uncertainty in our measurements. In writing our measurements, we have to be able to communicate where our estimation is. And that's where significant digits, or significant figures, and Sig Figs for short, come into play. So Sig Figs are how we represent that uncertainty. They show us where our estimation is and therefore how accurate the tool we were using to make those measurements is. In order to ensure continuity in communicating uncertainty, we have to have rules for identifying Sig Figs. All whole numbers are always going to be significant. It's the zeros that are going to be a little bit trickier. And so for those, we have a set of rules on when zeros are significant and when they are not. So the rules for determining whether or not zeros are significant are as follows. Zeros between whole numbers are always significant. Leading zeros are never significant. And trailing zeros are only significant if to the right of a decimal. Since those rules are a bit wordy and a bit complicated to understand, there's actually a shortcut that we can use in determining whether or not zeros are significant. The first thing to do when setting up our shortcut is to sketch a quick map of the United States of America, and then label the oceans on either side of America, the Atlantic and the Pacific. But in this case, our Pacific, our P, is going to stand for present, and our Atlantic, A, is going to stand for absent. And those are going to be in reference to the decimal in a number. So to use this shortcut, we look at a value and determine whether or not a decimal is present. If the decimal is present, we're going to move from left to right, from present to absent, or from Pacific to Atlantic, until we get to our first non-zero digit. And then we're going to continue counting from left to right, and all of those digits are going to be significant. If our decimal is absent, we're going to move from right to left, or from absent to present, Atlantic to Pacific, until we get to our first non-zero digit. And then as we continue moving from right to left, we're going to count all of those digits that come next, and they're all going to be significant. So let's take a look at a couple of examples. So for our first example, 0.453, our decimal point is present. So we're going to move from left to right, from present to absent, or from Pacific to Atlantic, until we get to our first non-zero digit. So in this example, as we go from left to right, 4 is our first non-zero digit. So we're going to keep moving towards the right and count every digit that follows because they're all going to be significant. So in this case, as we keep moving left to right, we are going to count the 4, the 5, and the 3. So 0.453 has 3 significant digits, or 3 sig figs. So in our next example, 13,400, there is no decimal place. Our decimal point is absent. So we're going to move from right to left, A to P, until we get to our first non-zero digit. So as we do that, once again, 4 happens to be our first non-zero digit. And as we continue moving left, now we're going to start counting all the digits that follow. So the 3 and the 1. So 13,400 also has 3 sig figs. Now it's your turn. Use the shortcut to determine how many sig figs are in each of the examples below. Pause the video, try it out, and then hit play when you're ready to check your work. All right, how'd you do? For the first one, there is a decimal point present, so you have to move from left to right until you get to your first non-zero digit and then count from there. For the second one, there is no decimal point, it's absent, so you have to move from right to left until you get to your first non-zero digit, which is 1, leaving us with just 1 sig fig. In the third example, again, we have a decimal point present, so when we move from left to right, our first digit is a non-zero digit, so we're going to count everything to the right of it. So this number has 6 sig figs. And finally, for our fourth example, once again, we have a decimal point present, so we move from left to right, and our first number is our non-zero digit, so we count everything thereafter, giving us 3 sig figs. The next thing to understand about sig figs is that when we're doing calculations with them, we have to make sure that we preserve our measure of uncertainty and that we're preserving our sig figs throughout our calculations. When we're adding or subtracting with sig figs, we can't be any more or less accurate than the number with the fewest number of decimal places. So our answer will have the same number of decimal places as the number in the calculation with the fewest number of decimal places. When we're dividing and multiplying, we can only be as precise as the least precise measurement. So our answer can't have any more sig figs than the number in the calculation with the fewest number of sig figs. So in summary, when adding and subtracting, go by the fewest number of decimal places. When multiplying and dividing, go by the least number of sig figs. Now let's do some examples to practice calculating with our sig figs. Try these 3 examples on your own, pause the video, and when you're ready, hit play to check your work. For the first example, we have a subtraction problem. So we're going to be using our decimal places as our reference. So when we do 3.4 minus 2.789, we get 0.611. But our answer can't have any more decimal places than our number in our calculation with the fewest number of decimal places, which in this case is just 1. So our answer can only have 1 decimal place. So we do a little rounding, and our answer to the correct number of sig figs is 0.6. For the next example, we have a multiplication problem. 300 times 4,390 equals 1,317,000. But since we're going by multiplication, we can't have any more sig figs than the number with the fewest number of sig figs, which in this case is 300 with only 1 sig fig. So we have to do quite a bit of rounding in this case, and our answer is going to be 1 million. Our final example actually has a combination of methods. We have addition, subtraction, and division. So which rule do we follow? Well, we kind of have to take this step by step and follow our order of operations. Remember, please excuse my dear Aunt Sally. Parentheses, exponent, multiply, divide, add, and subtract. So first up is our parentheses. 1.80 plus 70 gives us 71.8. But since we're adding, we have to go by decimal places, and 70 has 0 decimal places, so our answer can't have any decimal places either. So we're going to round up to 72. So next up on our order of operations is division. So we have to take 2.00 divided by 4.003, and we get 0.4996. But since we're dividing, we're going by fewest number of sig figs, and 2.00 only has 3 sig figs, so our answer can only have 3 sig figs. So here we're going to end up doing quite a bit of rounding too, since we're going from 0.4996 to 3 sig figs, which is going to be 0.500. So finally we're left with 72 minus 0.500. So when we do our subtraction, we get 71.5. But again, since we're doing subtraction, we have to go by fewest number of decimal places. 72 has no decimal places, so neither can our answer. So we can round up our answer to 72. So remember, when doing your calculations with sig figs, do your calculations normally first and then round your final answer based on the applicable rules, by fewest number of decimal places if you're doing adding and subtracting, or by fewest number of sig figs if you're doing multiplying and dividing. Finally, there's one other method we use when communicating our measurements, and that's through the use of scientific notation. Scientific notation is the shorthand used for writing very large and very small numbers. It consists of 2 parts: a mantissa that's always going to be between 1 and 10. It's never going to be less than 1 or greater than 10. And that mantissa is going to be multiplied by a power of 10. So for example, if we had the number 0.00458 and we wanted to put that in scientific notation, our mantissa would have to be 4.58, because that's the only number we can make that's between 1 and 10. And now we count how many places we moved our decimal place to get from 0.00458 to 4.58, and that was 3 spaces. And we need to multiply that number by 10 to the negative 3, because our 4.58 is larger than our original number. So we need to multiply by a negative exponent in order to make our mantissa smaller to get back to our original number. Conversely, if we wanted to take the number 48,800,000 and convert that into scientific notation, we would still have to have our mantissa between 1 and 10, so the only number that works in this case would be 4.88, and we'd multiply that by 10 to the 7th, because our mantissa is now smaller than our original number, so our exponent needs to be positive. Positive exponents are going to make our mantissa larger, and negative exponents are going to make our mantissa smaller. Finally, when combining sig figs and scientific notation, you're always going to look at the mantissa when determining your sig figs. And that concludes our discussion on evaluating measurements. Bring any questions you have with you to class.